Hi class, welcome to exercise 5e, factorising by completing the square. In this lesson, your examples and pre-learning will be example 12, completing the square. And your pre-learning for this example will be questions 1 and 2 in the new book and question 4 in the old book. And for example 13 will be factorising by completing the square. And your pre-learning for this example will be questions 3 and 4 in the new book and questions 5 and 6 in the old book. And then we'll do example 14, factorising with fractions. And your pre-learning questions will be 5 and 6 in the new book and 7 in the old book. So this is going to be a new technique to factorise any quadratic that can possibly be factorised with real numbers. This method is vital for the second half of this unit, which is graphing parabolas. Alright, I'll see you in the introduction. As an example of limitations of factoring by grouping, let's factor x squared plus 4x plus 5 with grouping. Now the factor pairs of 5 are 1 and 5 and minus 1 and minus 5. And of course we need one of these to sum to 4. But 1 plus 5 equals 6, which is not 4. And minus 1 and minus 5 is minus 6, which is also not 4. Okay, so let's go back to what we know about perfect squares, because this will form the basis of the new technique that we're going to learn today. So let's recall that x plus a all squared is equal to x squared plus 2ax plus a squared. Now you can find that by simply expanding the expression, but also recall that we can describe it visually as well, because a square with side lengths x and a obviously has an area of x plus a squared, but it can also be broken up into areas of x squared and 2ax because we have two rectangles of a times x and this little a squared here. Now what if we presented with x squared plus bx, which we can represent graphically with a square the size of x and a rectangle of b times x. If we break that rectangle into two and arrange it around x squared, and these sides are x, and these sides are b divided by 2. So you can see we've almost got a square of x plus b on 2. We're just missing this little square down the bottom here, and this must be b divided by 2 squared. So therefore, when we have x squared plus bx, if we add b on 2 squared, this is called completing the square. And let me just move that square so it looks clearer as an illustration. And of course, when we've added the b on 2 squared, we end up with x plus b on 2 squared. So for example, 8 divided by 2 squared is equal to 4 squared, which is 16. Or 5 on 2 squared is equal to 25 on 4. So this means that x squared plus 8x plus 16 is equal to x plus 8 on 2 squared, or x plus 4 squared. And similarly, x plus 5x plus 25 on 4 is equal to x plus 5 on 2 all squared. Of course, we can't just add a number to an equation without changing it, so please note that x squared plus 8x is not equal to x squared plus 8x plus 16, which as we know is x plus 4 squared. But x squared plus 8x is equal to x squared plus 8x plus 16 minus 16, because this essentially is just adding 0. And now we know this part here is x plus 4 all squared, but we've still got that other minus 16 there. So to put this in formal notation, when we have x squared plus bx, then we add b on 2 squared minus b on 2 squared, to get x plus b on 2 all squared minus b on 2 squared. This is called completing the square. Also note that this is true for negatives as well. So for example, x squared minus 6x is equal to x squared minus 6x plus minus 6 on 2 squared minus minus 6 on 2 squared. Notice how I've got the negatives in the bracket for the squares. So this means we now have x squared minus 6x plus 9 minus 9. Because minus 6 on 2 all squared is just equal to minus 3 squared, which is 9. So this means we now have x minus 3 all squared minus 9. So in other words, x squared minus 6x is equal to x minus 6 on 2 all squared minus 6 on 2 all squared, which is just equal to x minus 3 all squared minus 9. Now we can apply completing the square to any quadratic. So for x squared plus bx plus c, if we add b on 2 squared and subtract b on 2 squared, essentially we're just adding 0. But over here we've completed the square, and we now have x plus b on 2 all squared minus b on 2 squared plus c. So for example, if you had x squared plus 10x plus 13, because 10 on 2 squared is equal to 25, we can rewrite this expression as x squared plus 10x plus 25 minus 25, and of course still have that plus 13 at the end, because once again this is just adding 0. And this part here completes the square for x plus 5 all squared. So we're left with x plus 5 all squared minus 25 plus the 13. And so then we can finalize that as x plus 5 all squared minus 12. Now once we get to this stage, we can complete factoring using difference of perfect squares. So don't forget, that means that a squared minus b squared is equal to a plus b times a minus b. So let's start with the algebra version we finished up with there. And then by squaring the square root of the terms of the right, we've essentially not changed anything. So let's look at that where we've left the numeric version. So we square the square root of 12, and we can use difference of perfect squares at either stage here. So as I've written above, this would be the a, and this would be the b, and this would be the a, and this would be the b. Of course they're squared. Now, as far as this algebraic version goes, I'll let you complete that algebra. It's a bit brutish for me, but I can do this other one. That's going to equal x plus 5 plus the square root of 12 times x plus 5 minus the square root of 12. So here you can see our a and the b. Alright, so that's how we'll factor once we've completed the square. But what about our initial problem, where we had x squared plus 4x plus 5? So as b is 4, then we want to find 4 on 2 squared, which is equal to 2 squared, which is 4. So by adding 4 and minusing 4, we haven't changed anything, but we have completed the square here. Okay, so we've got x plus 2 because 2 is half of 4. So we're left with x plus 2 squared plus 1. But we've got a plus sign here, and we need a negative sign for the difference of perfect squares. So we need to rewrite that as x plus 2 all squared minus 1. And to factor x plus 2 all squared minus the square root of 1 squared, we run into a few problems because there's no real solutions for the square root of 1. And at this stage, we're yet to imagine what a possible solution could be. And so this initial problem demonstrates that not all quadratics can be factored. Because obviously we've seen we can't factor everything by grouping, so when we resort to completing the square, we rely upon difference of perfect squares. So if we complete the square and then we end up with x plus b squared plus c, and this plus c is greater than 0, then you have to stop until you know what the square root of a negative number is. But if we get x plus b squared minus c, and minus c is less than 0, so in other words, the c is a positive number, right? That means that we have x plus b all squared minus the square root of c squared. And then by the difference of perfect squares, we can factor that as x plus b plus the square root of c times x plus b minus the square root of c. Alright, there's a lot of dense information there, so I really recommend that you pause the video now and work on the building understanding questions, which translates to questions 1, 2 and 3 in the old book. As you know, we normally don't worry about the building understanding questions for your pre-learning, but it is really important to practice finding the right number to complete the square. Alright, I'll see you in the next section. Before you begin this section, make sure that you've attempted the building understanding questions. That way you'll know that because x plus b on 2 all squared is equal to x squared plus bx plus b on 2 all squared, and x minus b on 2 squared is equal to x squared minus bx plus b on 2 squared. If we have x squared plus bx or x squared minus bx, then adding b on 2 all squared will complete the square. Alright, let's just get straight on to example 12, where we're going to find the number to add that will complete the square, and then we'll factor the perfect square. Alright, part A, we've got x squared plus 10x. Now this means that b is equal to 10, and b on 2 squared is equal to 5 squared, which is 25. So therefore, x squared plus 10x plus 25 is equal to x plus 5 all squared. And in part B, we've got x squared minus 7x. And in this case, b is equal to minus 7. So b on 2 squared is minus 7 on 2 squared, which is 49 on 4. So that means that x squared minus 7x plus 49 on 4 is equal to x minus 7 on 2 all squared. And don't forget that that sign is really important. Alright, so that's it. It's really straightforward. So just pause the video now and do questions 1 and 2 in the new book and question 4 in the old book. And then I'll see you in the next section. Alright, as we've covered in the introduction, if we have x squared plus bx plus b on 2 squared, it factors to x plus b on 2 all squared. But if we have x squared plus bx plus c, and c is not equal to b on 2 squared, then if we add and subtract b on 2 squared, we don't change anything, because adding and subtracting the same thing is just adding 0. And as we've stated, x squared plus bx plus b on 2 squared is equal to x plus b on 2 all squared. Then x squared plus bx plus b on 2 squared minus b on 2 squared plus c becomes x plus b on 2 squared minus b on 2 squared plus c. Because this part here is just the perfect square, and of course we don't lose the bit on the end. And if the bit on the end, otherwise known as minus b on 2 squared plus c, is negative, then we can factor with a difference of perfect squares, i.e. a squared minus b squared is equal to a plus b times a minus b. Alright, let's go on to example 13, where we're going to factor the following by completing the square, if possible. Okay, and you know where it's not possible. Alright, part A, we have x squared plus 8x minus 3. So this means b is equal to 8, and b on 2 squared is equal to 4 squared, which equals 16. So this means that x squared plus 8x minus 3 is also equal to x squared plus 8x plus and minus 16 minus 3. Okay, because 16 minus 16 is 0. Alright, now this part here is actually equal to x plus 4 squared, and that should be a minus 3, by the way. And now we can move on with that. So minus 16 minus 3 is actually minus 19. So we can rewrite that squaring the square root of 19. Just as a side note, a square root of x all squared is equal to x if x is greater than 0. And 19 is, obviously. So now we can rewrite this as x plus 4 plus square root of 19 multiplied by x plus 4 minus the square root of 19 by the difference of perfect squares. And that's our final solution. You can't do anything with the square root of 19. Alright, let's move on to part B, where we have x squared minus 2x plus 8. Now because b is equal to minus 2, b on 2 squared is equal to minus 1 squared, which is 1. So we can rewrite the initial expression with plus 1 and minus 1, not forgetting the plus 8. And we could do this because we're essentially adding 0. So of course this part here is x minus 1 squared, and minus 1 plus 8 becomes plus 7. And you can stop right here. This can't be factored because we do not have a difference of perfect squares. This will become even more clear when we start graphing parabolas. Also, just want to add a pro tip now. You can still check your solutions when we've used a difference of perfect squares. Okay, so from A, we ended up with x plus 4 plus the square root of 19 times x plus 4 minus the square root of 19. And I just want to draw some brackets around the x plus 4s. And so we end up with x plus 4 all squared minus the square root of 19 times x plus 4 plus the square root of 19 times x plus 4 minus the square root of 19 all squared. Okay, that's just from FOIL. Now the two middle ones disappear because we've got exactly the same thing as plus and minus. So expanding our perfect square, we get x squared plus 8x plus 16. And the square root of 19 squared is just 19. So we have minus 19 at the end. X squared plus 8x stays the same. And 16 minus 19 is minus 3. And that's exactly what we want. Yeehaw. Alright, so pause the video now and work on questions 3 and 4 in the new book and questions 5 and 6 in the old book. And then I'll see you in the next section. Factoring with fractions is no different from the previous section, apart from a little bit more complication in the arithmetic and algebra. But all you need to do is find b on 2 and complete the square, and then factor with the difference of perfect squares if you can. Alright, let's have a go at example 14, where we're going to factor the following. X squared plus 3x plus a half. Now b is equal to 3, which makes b on 2 squared equal to 9 on 4. So we can rewrite the initial expression as x squared plus 3x plus 9 on 4 minus 9 on 4 plus a half. So therefore our first three terms make x plus 3 on 2 all squared, and minus 9 on 4 plus 2 on 4 is minus 7 on 4. So let me just write that out again. Minus 9 on 4 plus a half equals minus 9 on 4 plus 2 on 4. Because a half is 2 on 4, so then we've got minus 7 on 4. Alright, so we can now rewrite that expression with the x plus 3 on 2 all squared, but change 7 on 4 to the square root of 7 on 4 all squared. And the square root of 7 is the square root of 7, and the square root of 4 is 2. So let's rewrite that as the square root of 7 on 2 all squared. So therefore, we can factor that as x plus 3 on 2 plus the square root of 7 on 2 times x plus 3 on 2 minus the square root of 7 on 2, just using the difference of perfect squares. And we've got two things here on 2, so let's rewrite that as x plus 3 plus the square root of 7 divided by 2 times x plus 3 minus the square root of 7 on 2. I think that's much neater. Alright, and that's as far as we can go with that. Just want to give you one more pro tip, and that is as long as you stick to the formula, you can complete the square with any trinomial ax squared plus bx plus c. Except that so far you've only used a equal to 1. So in the case that a is not equal to 1, then you have this ax squared plus bx plus c. You can rewrite that as a times x squared plus b divided by ax plus c divided by a. Just factoring out the a. Then inside those brackets you can add a b divided by 2a squared and subtract a b divided by 2a squared. Still adding 0, but remembering that b divided by a, all divided by 2, is actually equal to b on 2a. Now of course everything's still going to be multiplied by a, but these three terms here have become x plus b on 2a all squared. And these last two terms haven't changed at all. And obviously we've still got the a factored out, so we need to multiply it across. And this formula that may look a bit complicated, but I hope it doesn't for you right now, will form the basis for our final lesson on quadratics. Anyhow, we've gone a long way here. Don't forget that this section is just about using fractions, okay? So just use what we used in the previous section. Don't get confused by the fractions. All right, pause that video now and work on questions 5 and 6 in the new book and question 7 in the old book. And then when you come back, we'll summarize this lesson. Okay, we've reached the end of the first block of this unit. And so far, you've learnt how to factor by difference of perfect squares, grouping, and completing the square. Mastering them is vital because the rest of our unit will be applications of quadratics, extending the theory of completing the square, and finally graphing quadratics with what we call parabolas. So please make sure that you've put all the effort in that you can to master these and get all the help you can. Anyhow, from this lesson, a successful student will know the expanded form of a perfect square, be able to carry out the process of completing the square, know how to factorise by first completing the square, and finally, understand that not all expressions can be factored. Alright, so that's the end of the lesson. Make sure you do master all of those key skills. I'll see you in the next lesson or in class. Bye.